Today's daily code problem of the day is largest combination with bitwise and greater than 0. First thing for this problem is I'm going to explain what a bitwise and operation is. So, bitwise and. A bitwise and operation simply is an operation, an and operation, just like our Boolean and operation, but instead of using two and symbols, we're going to use one symbol in Java. And this operation is going to check the bits and compare the bits of two numbers. So if we say 3 and 5, like the example here, we have 3 and 5. We're simply going to check the bitwise representations of each number. So the bitwise representation of the number 5 is 101. The bitwise representation of the number 3 is 011. So for each of these numbers, we're going to look and we're going to AND their numbers. So 1 and 1, well, the result is going to be 1. We have 0 and 1 because it's like comparing a true and a false. And let's say the zeros are false. So we have 1 is true, 1 is true. So we're going to get 1. 0 is false, 1 is true, we're going to get 0, false. 1 is true, 0 is false, we're going to get 0, false. And that's all a bitwise AND operation is. We're going to look at the bits of each number. If it's two matching 1s, the output's going to be a 1. If it's a 0 and a 1, the output's going to be a 0. If it's a 0 and a 0, the output's going to be a 0. Simple as that. So for this problem, we're going to use the bitwise AND, and we're going to use it on an array of nums, and we're going to check the bits between all these numbers. The goal for this problem is to evaluate the bitwise AND of every combination of numbers in our candidate list, and we are going to return the largest combination of candidates with a bitwise AND greater than 0. For a bitwise AND to be greater than 0, all that is required is for a single 1 to be present in the output. 0 is all 0 bits. So as long as we have a single 1 in our bitwise representation, it is greater than 0. So for our approach, we are going to first initialize a counter, and we'll use this to track how many of each bit is available. So I'll dive deeper into that in a second. We'll then count set bits, and then we will determine the max count. So when we're initializing our counter, what exactly is this counter doing? It is going to keep track of how many bits are in each position. So let's say we're going to have 32 bits. That's the max number we can deal with in this situation. It doesn't say it, but you can assume it. That's the max amount of bits in a number. We're going to keep track of how many of each bit is a 1. So in our array, let's say this is our counter array. There's 1 bit that appears here, 5 bits that appear here, 2 bits that appear, or 3 bits that appear here, and 2 bits that appear here. That's how we're going to keep track of it. And depending on how many candidates we have, let's say we have 5 candidates, the biggest subset we can make is 5, because there's 5 bits here. Let's say the biggest, or we have 10 candidates. Again, still the biggest subset we can make is 5, because they all share a common bit right there. So let's go ahead and start coding this. So we're going to first have an integer array called bit count. It's going to be equal to a new integer array. It's going to be a size 32 because that's the max number of bits that we can have. We're now going to count our set bits, and we'll do this by iterating over each integer in our candidate list. So for int num in candidates, we're going to then iterate through each bit in each number. So for int I is equal to 0, as long as I is less than 32, I can increment And we're going to check if the ith bit is set, meaning that it's a 1. So if num, we're going to and operation it, and its 1 value shifted to the left by I positions, and it's not equal to 0. So we're checking if the I value, or if the I value is shifted to the left, however many positions we are looking at. So if I is 5, we're going to say whatever our starting position shifted over to the left 5. As long as that position is not equal to 0, we can increment our bit count. So bit count of I is going to be incremented by 1. So the reason we're using this technique, it's a bit mask technique, and we're shifting a bit over I positions. The reason we're using this technique is it allows us to continue to use the I value to keep track of our bit count array. So that just makes it easier for us to manipulate both the array and our number. We'll then have an integer max count. This max count is going to find our maximum value, and we'll do that by seeing if there is the highest number of bits in whatever position, as long as it's greater than 0. So we're going to return max count after we do for each integer count in bit count. If count is greater than max count will be equal to count. As simple as that. And then we'll return our max count. So if we run this, passes our test cases, and if we submit it, passes all solutions. So the most confusing part about this solution is this expression right here. So I thought I'd explain it a little bit more. So this part on the inside, the 1 left I, is a left shift. So the expression 1 left I shifts the binary representation of the number 1 to the left by I positions. In the binary 1 is represented as 0001. Shifting it left by I positions results in the number where only the ith bit is set to 1 and all other bits are set to 0. So by doing this, it makes it easier to compare each bit of our number with the corresponding bit of I shifted left, or 1 shifted left I times. The result has a bit set to 1 only if both corresponding bits and the operands are 1. So otherwise the bit is going to be 0. It's simply a way to check to make sure that the ith position of num is equal to 1. So we're comparing a number that is for sure a 1, which is going to be 1, and we're checking the ith position in num to see if that's also a 1 and not a 0. So that's it. Thank you, and follow for more daily LeetCode solutions.